the next one. But as a start, I'm really happy to welcome not Chris 1, but Chris 2. It's a joke in between us. So Chris 2, welcome to the TAIAO workshop. And I've been looking at, because I didn't know you before, and I was really surprised looking at your bio. You've got a double PhD. Wow, look at that. Not one, but two PhD for Christo. So one in applied mathematics and one in process and environmental engineering, chemical. Is it like one?
That's the first PhD.
Oh, the first
Second one is in coastal engineering with
coastal engineering. Awesome. And you are working for NIWA.
Yes.
Very good. It's all yours.
Awesome.
Thank you, Christo.
Thank you very much. Is this my presentation or the one that you guys are? Oh, that's all good. Yeah, good morning, everyone. Thank you for the opportunity to share some of the work that we've been working on. Just a disclaimer, I had a bit of a cold, so my ears are still blocked. So if I either scream at you or can't hear you, please just bear with me. Yes, I'm Christo Rautenbach, work for NIWA. We've got a coast and estuaries physical processes group there. And we do a broad range of research. And this topic kind of came about exactly like Karen was saying, co-developed. It was a need that was expressed by Surf Lifesaving. And we tried to think outside of the box of how we can actually address their needs. Typically, we're more numerical modelers in our group. So artificial intelligence didn't necessarily come naturally to us. But we think this actually worked pretty well. So I'll walk you through it and welcome any questions. Oh yeah, and I have to acknowledge, it's not just me, it's my co-authors as well. So, because we're a diverse kind of audience, I also thought, let's just go over what a rip current actually is. So, who knows what a rip current is? Or, wait, let me reformat. Who's confident that if they go to a beach, they can identify a rip current? 1, 2, 3, 4, 5, 6. So that in itself shows that, and who goes to the beach? Well, there you have the statistics. And that's kind of the problem that Surf Lifesaving came to us with, is that even amongst people that say they can identify rip currents, Surf Lifesaving did some research and they found that 80% of those people couldn't actually identify a rip current. So hence why rip currents are still the #1 beach hazard that we're not facing just in New Zealand, but all over the world. And there's two aspects to this, right? It's forecasting and identification. But to be able to forecast, we need to first actually have a method that we can readily identify this and not torture some students by clicking through thousands of images. So kind of getting that done easier. So a rip current is a strong, localized and narrow current of water which moves directly offshore, usually. From an aerial point of view, you can spot them. It's usually where there's no waves, usually. And of course, coastal processes are more complex than that, so these are gross simplifications, but that's what it kind of comes down to. They tend to be the strongest and fastest near the surface of the ocean. And like I mentioned before, they're absolutely deadly with regards to beach hazards. In 2013, they were found in Australia to be killing more people than bushfires, floods, cyclones, and shark attacks combined. So definitely something that needs attention. So while lifeguards are very good at detecting rip currents, most people can't detect rip currents like we went through just now. But the majority of the drownings actually occur on unpatrolled beaches. So how do you then, so Surf Lifesaving can only reach that far. And then the numerical process of rip currents for those into numerical modeling is very difficult because the morphology, so the morphology you can say is the beach, the sand shape and changing of it is very chaotic. So it's very difficult to actually predict accurately. with numerical models. And that's why we thought, okay, what do we have at beaches? We've got cameras, usually. And if we don't have cameras, we could kind of come up with a methodology where we do have cameras. So that's why we thought, okay, maybe not numerical modeling in this case. So basically our aim was to take beachgoer safety from the reactive to preventative, you know, so not get people in trouble and then go and save them, try and prevent this. This will also require a clear and efficient way of warning and notification dissemination, which kind of links back to the co-development with people that actually know how to work with beachgoers and the communication of science. And the aim was then for the accurate forecasting eventually, and identification of rip currents to inform the public where rip currents were occurring so that they make informed decisions with where to swim. So in general, just please swim where the lifeguards tell you to swim, but still. So and then with regards to artificial intelligence, which I think the audience know can teach me a lot more about, but nevertheless, it's basically a process of where we're trying to take images, which is taken from a video camera or still images. And like those, the animation to the left, for us, it's very easy to see which number that is, but it's not always that simple for a machine. And our training process is actually just going deeper in the convolutional layers to a point where the AI can readily identify what we're looking at. But all we're doing in this case is the same as those numbers, but a rip current. The reason that was quite tricky is because rip currents is what we call amorphous. So they don't have a fixed shape. They don't always have the same characteristics. So how the flip do you then train that? And that's what we try to tackle here. We also didn't want to define bounding boxes because, like you'll see later on, we're hoping to use drones and moving images as well. So then you can't just keep on defining a box to actually identify where the rip currents are. So we used interpretable artificial intelligence. Within that, we used Grad-CAM, which identifies the pixels of greatest importance to the model output prediction. I think we saw just earlier in one of the presentations a similar thing. So basically, where the colors are warmer, that's the pixels that mostly help the AI to say that's a cat or a dog. And we're going to do the same with rip currents. And this helped us to actually see, because we can see what the AI is looking at to make its determination, that helped us with the interpretation and helping the machine to learn. But we'll get back to that. So, what is interpretable artificial intelligence versus just artificial intelligence? Basically, in this diagram, the first column is where you've got your massive amount of training data, your model, and you end up with predictions. But what we've built in is just this extra loop to interpret it. So basically, an expert user, myself and Nilesh, my colleague, will actually look at if it's a positive and a negative identification of a rip current, actually see, did it look at the rip current to make that call or not? And that actually helps us. It's like a semi-supervised learning. But that helped us to see in which aspect is this machine learning still failing so that we can add more intelligence, basically training it more of the right stuff so that it gets smarter, if that makes sense. So what that means is what we've seen is that the predictions were sometimes right, but it was making the right prediction for the wrong reasons. So for example, in the beginning, it didn't have enough intelligence, so it saw rocks, and then it thought, oh, that's a rip current. But coincidentally, there was a rip current, but the reason it made that decision was for the wrong reason. So that's a no-go. So rocks was a big problem, and also people. And then we realized, oh, flip, we actually didn't have enough images with people on the beach. And all these other things also come into play. So fog, rain on the lens of the camera, angle, shadows were a big one. Vegetation, because you can imagine if you take pictures of coastlines around the world, even beach color We've got black and white sand beaches in New Zealand, you know, so all of that had to be incorporated to make it smarter and smarter. The age-old rule of garbage in, garbage out counts pretty much with any science and any model. So we really want to make sure we're not sending garbage into the model. So we try to look at different criteria for training. So we looked at a diverse range of coastlines, like I mentioned before, to make it more general. Diverse range of tidal conditions, because that's the other thing. Your beach size changes based on the tidal phase. And then the beach color and everything associated with it also changes. We looked at a diverse range of environmental conditions: fog, rain, storm surge, sun glint, shadows, and calm weather. Even if you train the model just on storms, you'll run into problems, because then when it's calm, it's freaking out, not sure what's happening. And then camera angles was a really big thing. I should have brought a pen of paper. But surf lifesaving's number one requirement was actually, maybe I'm jumping the gun a bit here, but they wanted this tool or app to be able to identify rip currents from beach angle. But the problem with that is, if us as humans can't see a rip current, the AI won't be able to see a rip current. So if you're so oblique that you can't actually see, especially if the waves are calm, if there's a rip current, the AI can't just magically make up information, you know, so that's much more tricky. So technically, beach angle, we generalized enough that it doesn't matter, but to a point. So you can't just stand on the beach and take a picture, for example, but we'll get back to that. So I'll get to our actual data set just now, but we also generated more from less. So we use different online packages to synthetically generate even more images. So we blurred images, we changed the perspective, we added random shadows and fog and everything. So we literally made our training data set artificially a lot bigger. And that helped our accuracy a lot. So we found that even though these weren't necessarily real images, the concept of it at least helped the AI to understand that this is not a rip if it sees it in a real life situation. So we used a convolutional neural network that learns to extract information through convolutional kernels or weights. Things like edges becomes important. It learns to tune these weights through the training data, and that's why all of the generalization and diversity of training data was so important. So beyond all of this, we also use a technique called transfer learning. So we didn't start from scratch. Transfer learning carries knowledge from one model to the other. So if you look on this right-hand panel, the traditional way is that you've got one data set and you create one model, second data set, second model, but we actually use the knowledge from a previous model into our model. So I always explain to people, it's almost like the way I see it is, we already had a brain and we just added a very specific part of the brain that could specifically be more intelligent for coastlines. So our data. Obviously, then we had heaps of images with and without rip currents. But more specifically, the knowledge that we got for the transfer learning, the previous model, was trained on ImageNet that consists of 1.3 million images with over 1,000 different categories. So it could already mostly identify dogs and cats and houses and cars and everything that's not amorphous. And then our intelligence we added with the open access library of aerial images. So directly from the top, not at an oblique angle. But then we did those augmentations that I spoke of to kind of compensate for that. That aerial image library consists of 1,700 images of rips and 700 images without rips. And we did our validation on the oblique angle because that's more realistic. Either you'll have a fixed camera somewhere or Unless you're using a drone, it will be aerial, but nevertheless. And then the question was, could our AI model generalize aerial to oblique well? This is kind of the summary. So our model accuracy ended up being approximately 91% of oblique on the oblique image test. Transfer learning and data augmentation increased the skills significantly. So when we just had the convolutional neural network, we were just shy of 60%, which is really bad because it's almost like flipping a coin. When we added the augmentations, we went into the 70%, which is great. When we just had transfer learning, it was a bit less, but when we added transfer learning and the augmentations, it went really up a lot. Accuracy, I mean. And then hopefully this plays now. There we go. So this is what it then ends up looking like. So if, say, for example, you've got a camera somewhere monitoring a beach or a surf cam, this was some of the results that we got. So where it's red, it's important for AI to make its call. And usually it gives a confidence margin as well. So you can, so as a researcher, you can also set that, you know, like above which confidence would it mean, would you be happy to let Surf Lifesaving know that this is a rip current? On the social side of things, wait, I'll get to that maybe a bit later, but maybe just mention it, is that this is also the information that we won't just directly disseminate to beach users immediately. The next phase of this project would be that this is a background tool to empower surf lifesaving first. So that if the drone or a camera identifies a rip current where the lifeguards didn't see it, they can actually go and check if it's actually a rip current and then take the appropriate actions. And in return, add a tag that there was a rip current. So there's two things. It helps us to ground validate this method at different beaches around New Zealand, but it's also increasing our data set even more. You see the waves are confusing it a bit there, but mostly it's identifying it for the right reason. These are more aerial images. So then also the next question is this better than what we were using before? So image processing in the coastal zone is actually really well established, and there's been a lot done in the past. So it's definitely not a new thing, but in our paper, we also spoke about that, where there's pros and cons with regards to any method. The big thing with regards to artificial intelligence is that what we found, it's kind of limited to what it's seen before. But this artificial, or the interpretability of this method allows us to add even more of our specific knowledge to help the machine. And yeah, but unlike numerical models that solve the physics, if it hasn't seen something really, it can't predict or identify it. So that's one of the problems with our method. The other method is cumulative breaking portions using image analysis through MATLAB or Python or whatever your tool of choice is. It uses a series of images and averages it usually to calculate the cumulative breaking portion, which could be used as a measure of motion. So if you look at the right-hand panels, the color scale is just reversed. Sorry about that. So basically, where it's warm colors, that's kind of where most of the waves are breaking. So you're looking for the areas where there isn't warm colors. That's probably the rip. While our method was just, it actually identifies the rip current. To a degree, because you're more involved with data processing, these techniques offer more flexibility depending on what you actually want to do with the images. As coastal engineers, we're always interested in beach volumes and beach width as well. So it's not just using images for rip current identification. So if we can do more things with the images, it's also very beneficial, also to regional councils and councils. Oh, the image averaging techniques are a bit challenging in the sense that it's more difficult to roll out real time. While this method, this AI method of ours, it's more easy to just, you know, disseminate it and roll it out. Okay, so in summary, interpretable AI model generalized from aerial to oblique imagery with the accuracy of around 91%. AI models enable rip current localization without annotation or bounding boxes. Data augmentation and transfer learning are critical to improve model performance. The interpretable AI enables better model data development. If you're interested in more of this information, we published basically this whole methodology last year in remote sensing, and I can share that paper with whoever is interested. So the next step is basically we did this work and we wrote that paper almost just as a proof of concept to show that in theory this is a potential approach, but currently it's not really being used anyway. So at NIWA we've got a network of cameras around New Zealand. So our first plan is to use the cameras that's actually pointing at the ocean in an appropriate direction and deploy this to try and see, you know, is it actually useful? But that whole system isn't operational, and it's not necessarily feeding back to surf lifesaving because our cameras are more where there's coastal erosion problems rather than, you know, beaches where people swim and things. So together with the co-development, oh yeah, should have mentioned this. So we've really co-developed all of this with surf lifesaving from the beginning. We've got a memorandum of understanding with them, and yeah, so we didn't just run into a direction and came up with the requirements. We actually worked with them every step of the way. It's actually their need that we've tried to address. So they also suggested the next step would be to really see if something like drones would be a good possibility. Across New Zealand, that does not necessarily mean it's a good option because you have to consider the sound of it. The beach will the community and be happy with that. So there's a lot of community engagement per beach to actually determine what the best solution for that beach would be. But because most drownings actually occur at on-patrolled beaches, it could be a good solution. Who did we talk to? Some of the beaches actually recommended that they would prefer having like a little buggy or rover patrol the beach with a camera on a high pole, actually looking at the ocean. That would be more acceptable. So that we still have to explore. So Surf Lifesaving also has this app called the Safe Swim app. If people don't know about that. They're already communicating various warnings and hazards through the Safe Swim app, including some water quality predictions, especially at the swimming beaches. And the idea is that if we progress per beach with deployment of this technology, that the information will be fed straight through the Safe Swim app, either to users or to first Surf Lifesaving, like I mentioned before, and then directly to users. And then we'll definitely explore Adam Willer, which is the CEO of Surf Lifesaving. He wants people to just hold up their phone and point at the ocean and then see, oh, red, there's a rip current and things. But let's see. The other thing that we're really planning on doing is to build a rip current hazard forecasting tool. So all of this is identification, right? So it's real time. We see the rip current now, we respond and activate now. While you probably want to know, are there rip currents going to be there tomorrow? Now that's very difficult to predict because it's not like a wave climate. It's not like winds that we can forecast readily because there's very local morphodynamic processes that can determine the formation of a rip current. But there are indicators of a probabilistic increase in the odds of a rip current occurring. And that's what we're trying to build, is we're going to try and see, given the tidal level, offshore wave climate, wind conditions, what's the odds of a rip current occurring on this specific beach, and then feed it through the same app. And then continuously adding to the largest identified rip current repository through collaboration with localizing, because every rip current that we correctly identify or don't identify adds to our repository. It's my last slide, guys. Almost there. In any case, I can talk to the slide in the meantime. So the key to the success of these type of technologies is definitely transdisciplinary research. So, or what we call co-developed research. So it's really making sure that the communication of science to the stakeholders is done efficiently. So in the past, things that we've done is, for example, we looked at marine meteorological forecasts for coastal ocean users, the perception, usability, and uptake. And in that was a very much a social science study that we've done. And there we really looked at what are the factors that actually determine that people trust a product, that people use a product, especially when we're looking in the forecasting space. Believe it or not, we asked a lot of very tricky questions that people can't readily see what we were after. But what we found in our modern communities is people trust apps blindly. The reliance on the scientists and the institutions behind app development has been kind of released. The majority, the main thing that determines that people would use technology or an app from that study, that survey, and we did it in 2 countries, as New Zealand and South Africa, for obvious reasons. The main driver of people's trust was how the app looks and functionality, and if it's sexy. So and that is a big lesson. Like if people open an app and they have to click more than 3 or 2 times, and it's cumbersome and there's a graph and you have to scroll, done. They'll never use it again. So yeah, I'm just wanted to highlight that to all of us to make sure that we actually understand our users. And then there's other opportunities. So another study that we did in South Africa was to connect search and rescue information. So if there was an incident in the ocean, so someone fell overboard, fell off of the kayak, any incident where they needed rescue, we didn't use AI, but we used just statistics to connect those incidents with the predominant mid-ocean climate, and found in some instances very strong correlation. So it kind of starts making it predictable. So it again points towards the predictability of things that's actually otherwise quite difficult to predict. And that's why I see our next steps are. And that was all I wanted to share. Thanks, guys.
Thank you very much, Christo. Very interesting, really like it. I think if we've got time, I don't know if you want to take any question or start a conversation. We got a few minutes if you are interested in Christo research, what he is doing at NIWA. And maybe that's a good opportunity. A lot of AI experts as well in the room, making good connection with the work NIWA is doing. Yes, please.
Yes, I will greatly ask. So thank you for your presentation. I actually learned a lot. I wasn't aware of the current at all. So, obviously, you said that recurrent is forming, similar environment, and I guess that mostly on surf beach. So I was wondering, if possible to enrich your data set using also satellite imagery, like for more long-term, identification of places that are more likely to have recurrent, and you try this or explore this.
It's interesting you recommend that, because we applied for Smart Ideas grant last year, and that was part of the reason I rejected it, because they said we didn't consider satellite images. But the reason we didn't consider it is just the frequency of the satellites. So even if we were to use satellites that comes close to maybe the appropriate time interval between taking images, it's way too expensive. So we can't afford it, and definitely no grant will be able to buy those images. For the images or products that is available, maybe one a day or two a day, while these things change per half hour, hourly, per tidal movement, you know. So the frequency of that type of remote sensing is just too low. And in a lot of cases, the resolution is too low. So you're looking at way too much zoomed out. Again, it's location specific and it's RIP specific, because some RIPs are massive, but mostly the ones that we're looking at is really right in the surf zone. It's very localized. So it's both the temporal and spatial resolution is too low.
Thank you. Yes, Barbara?
Yes, how often will the city currents occur in the same place at the same which?
How often does rip currents occur in the same place? It depends. So Raglan, there's a few spots where there's almost always a rip current. And then other beaches, it really depends on the season. So in winter, in general, you've got a more active beach. There's a lot more storm waves coming in. So your beach becomes steeper and narrower. So your probability of rip currents become probably higher. But who swims in winter? I mean, there are some freaks, but then they know what they're doing. Yeah. So it depends. I mean, that's a stupid answer, but it depends. Some places it's very reliable, especially next to coastal engineering interventions. So things like groins, there tends to be a rip current, and surfers actually use it to get behind the surf zone. You know, so it's not always a negative thing. Surfers use it a lot to kind of, then they don't have to paddle through and over all the waves. But I guess the most dangerous ones are those ones that just appear because the tide is coming in or out. And you've just been swimming here and there was nothing. And then suddenly you're like, oh, why am I going deeper, deeper, you know? And some of these rip currents are stronger or faster than an Olympic swimmer can swim. So even if you think you're a good swimmer, if you battle those bad boys, you're going to lose.
Thank you. Yes.
So you mentioned that in the literature, the best results we found was 95% accuracy, but it was not really interpretable. So do you mean that basically Grad-CAM cannot really be applied to it?
So we use Grad-CAM, but their method, it could be used. They just didn't. They had a defined bounding box. So they used a different method of annotating and saying that in this specific box, we're only looking for rip currents. So it's almost like making the problem a bit smaller, but can be used. Yeah. So that was just our departure point. We didn't want to reinvent the wheel. So we started from their study, which was a PhD study in America. And they had like 95 or higher % accuracy, but the generalization was a bit more tricky.
I see exactly what they're saying with that. Well, if they already have a well-defined bounding box, it makes the problem a lot easier.
Yeah.
Yes, I agree with that. So, by the way, just out of curiosity, so what's the data set size you use for?
So ImageNet was 1.3 million images. That was the general one. And then ours was, what was it? 7,000? Not that big. Also because we were doing this on a shoestring budget. So we were like, okay, we can only do that. We had 1,700 images with 700 positively identified RIPs. So that can be increased a lot. But I mean, so at NIWA, we get a bit of funding from the state to do public good research. And I snuck this whole thing in through that. So we didn't have actual funding. So we couldn't just sit there for days like, yes, yes, no, 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 yes, no, no, you know, so.
Didn't work. Actually, you're taking any summer students to do the job?
We got an intern that started helping, but I think he ran out of steam quite quickly as well.
Karin.
I know that you didn't use averaged images, you only used the real one, but I think even if you averaged 10 seconds prior, so that it took out those waves, that might be worth.
100%. So I'm not sure if you guys heard. So Karen suggested that we still use some sort of pre-processing, so averaging 10 seconds of images and then doing the identification. 100%. So this is not a 100% refined methodology whatsoever. This was almost just like a stake in the ground to say, in theory, it's a minimum viable product. It looks like it can work, but there's a lot of refinement in the methodology, in the AI as well, and in the deployment of the technology.
Good. Yes, correct. Yep.
Oh, so to use video clips, yeah, we haven't done that. So we trained it with still images just because it gave us more control of positive, negative. And then we tested it on videos and images, and then it was just easy because we just run it through, you know. But definitely that could be very interesting. It's not our method. It was so Tom Shand from Auckland University. He's been working in coastal image processing for many years. So that's more various things that he's extracting. They do averages and that's usually more still images because these cameras don't run off a constant power supply. They usually have some solar panel thing. So they'll activate on the hour, take 10 images, switch off, you know, that type of thing. And then those 10 images are used for averaging and those type of things.
Cool. Thank you. Yes. Bernard. Oh, sorry. Abe. Bernard is here.
Has anyone looked at when you're using feathered balloons or kites to suspend the camera in the air and monitor the each level?
Not that I know of. So, yeah, I mean, that's why we were thinking drones, because drones you can at least program the flight path, you know, so especially if you take a beach that you know that's very big in expanse. Usually the lifeguards are right by the parking and the beach access. So my idea was that the drones can just be programmed with its path, take off once an hour and mission, go all the way down. While balloons, I guess in the beginning you'll see a lot and then less and less, and then you go to the satellite problem.
Sort of stationary, I guess there's a lot of wind, which might blow the balloon around a little bit. I mean, usually the lifeguards have a building, right? So you could attach the balloon to the building.
Yeah, could be.
Right.
Yeah. I mean, with other beach process monitoring, usually they want the images so still because they're counting pixels that's geo-referenced, you know, so for beach width and things like that. So if a camera even like zooms and tilts and stuff and it comes back, it's 3 pixels out and then they lose their minds. Well, this, it doesn't, thank goodness, it doesn't matter that much, you know, so if it's moving or if it's a drone or something, it should be fairly okay.
I from the presentation, I presume you use mobile net for your model. So have you considered some of the neural architectures, like say, well, in our experiment with the species classifier, we found that say the second version of MixNet seems to work relatively well, and that's basically also small and efficient enough to be loaded on a cell phone. So, and then also like with ImageNet, there's actually a larger version of ImageNet that has 21,000 passes and a lot more. Well, I can't remember, but a lot more than 1.3 million users. So, like say the ImageNet version 2 comes with pre-training with the 21K version of ImageNet as well. So. I wonder if that would be something that was trying.
100%. So basically, we parked this whole research topic now because we ran out of money. So NIWA allowed us this little chunk of research stuff, and I could prove and get all of this up and running. But now we're kind of running around like headless chickens looking for money and then ideas, because I'm not an AI specialist at all. But I think it's just all this is just to show that there's heaps of potential in this space. and with obvious impact, you know, saving lives.
Very good. A last quick question, Karin.
There's a quick comment. I just wanted to say that there's probably quite a bit of international business opportunities with it. Because I remember 15 years ago, I got a big contract for a Dubai municipality to actually digitize the location of rip currents for hotels, you know, those really quite wealthy hotels. And so, I mean, that was really manual, but they really value that information as being a part of the package they give to tourists.
Oh, wow.
Yeah.
No, thank you. That's a great comment.
Thank you again, Christo.
Thanks,
Maybe we got a time. So are you staying with us for the day?
Yes.
So will be a lot of time for you to catch up with
Yes,
Christo.
100%.
We have to keep going and get to the first one. I would like to help me to clap some more claps for Christo. Amazing presentation. Thank you.